All right, I'd like to work through the kinetics quiz that you worked on recently and take you through the answers on this, explain how I would answer them. I don't plan on the video here to do a lot of reteaching of topics, so if there's a question that as I answer it you're not sure where that's coming from, just make note of it in your own work and touch base with me whenever you get a chance about further explanation on that. Just to keep the video reasonable in length, I won't try to reteach everything as we get to the questions any more than I absolutely have to kind of explain the answer. So question 1 gives us a reaction of X and 2Y forming Z. Everything's a gas. The reaction's at 25 Celsius or at standard temperature, and they're giving us in the experimental rows here the concentrations of X and Y are two reactants, and they're also giving us the rate of the reaction in terms of the formation of Z, how quickly Z is being formed, or how quickly the molarity of Z is changing per second. And so an initial rate of the formation of Z is given there for each of the three trials. Remember, the initial rate of the reaction is always the fastest because as the reaction takes place, the rate of the reaction slows down. While the particles are used up, there are fewer and fewer collisions, and so the reaction rate eventually slows down and kind of levels off at a particularly low level, but at first it's fastest, and that's when it's typically measured when we're looking at data like this. So in A, I want to determine the order of the reaction with respect to each reactant. That means holding X or Y constant while I manipulate X. So in trials 1 and 3 here, I'm going to pick out those. I can see that in trials 1 and 3, Y is constant, while X is doubled. And then what's happening to the reaction rate here? Reaction rate is doubled as well. Therefore, the reaction is first order with respect to X, the thing I'm doubling. For Y, I want a trial, two trials where Y is changing but X is constant. So I'm going to use trials 1 and 2. X is constant. Y is doubled. And again, the reaction rate doubles in those two trials. So the reaction is first order with respect to Y as well. So first order with respect to each. The rate law then would be rate equals K, don't forget my K, X to the first, Y to the first, or just X and Y, like so. To find the rate constant K, I want to rearrange that equation. It'll be rate over X to the first, Y to the first. Take any row of data that you want. I'll take row number 1, 1.20 times 10 to the negative fifth. That's in molarity per second. X in trial 1 is 0.2. Y is also 0.2. So as I go to my calculator, punch that in, it comes out at 0.00030 0 sig figs, or 3.00 times 10 to the negative 4. And then the units on that, let's see, molarities cancel. I'm left with molarity to the negative 1 and seconds to the negative 1. The initial rate of disappearance of Y in experiment 1. So the rate I'm given in experiment 1 is 1.20 moles per liter. That's moles of Z per liter per second. It's moles of Z, formation of Z. So it'll be moles of Z per liter per second. That's the forming of Z. The ratio I need is this one. In this reaction, it's a 2-to-1 reaction. So there'll be 2 moles of Y used for every 1 mole of Z formed. So I'm going to take that 2 moles of Y will be used for every 1 mole of Z that's being formed. And moles of Z would cancel out, leaving me with 2.40 times 10 to the negative 5. And that'd be moles of Y per liter per second. So that'd be my rate of Y being used, rate of disappearance. All right, that's D. E, in a closed 2.5 liter vessel at 22 Celsius. This sounds like a, this sounds like a volume and a temp, and that automatically says maybe ideal gas law is going to be useful. That's often the case. 0.0254 moles of X reacted with 0.0495 moles of Y. Determine the limiting reactant, assuming the reaction goes to completion. So something's going to get used up. And there's my reaction equation here. X plus 2Y makes Z. Everything's a gas. Okay, so X plus 2Y makes Z, and they're all gases. And I have 0.0254 moles of X, 0.0495 moles of Y. So to find the limiting reactant, I'm going to just pick one of those and figure out how much of the other one I would need in order to use it up. So I'm going to say for the 0.0254 moles of X, how much Y would I need? According to that reaction, I'll need 2 moles of Y for every 1 mole of X. And that's from my equation up here. Not the order of the reactions that we figured out earlier, but the ratio and the coefficients here. So I'll need 0.0508 moles of Y in order to use up the X. That's to use all of the X. Do I have that much Y? I do not. So Y is going to run out before X can be used up. That means Y is the limiting reactant. As the this amount is not available. Okay, so Y is the limiting reactant. Calculate the number of moles of Z formed. So I want to start with my limiting reactant then from that point forward. 0.0495 moles of Y will be used up. That's the limiting reactant. How much Z will be formed? According to this reaction, 1 mole of Z is made for every 2 moles of Y that are used by the reaction. And so that comes out at 0.0248 moles of Z will be formed if I round it off to 3 sig figs. And then calculate the total pressure in the flask at completion of the reaction. So I think I want to use a rice table for that. That'll help me out to kind of organize what's being used here and what's left over. So it's kind of crowded here for my rice table. Go back up to my reaction equation here at the top. And we started out with 0.0254 moles and 0.0495 moles and 0 moles of this. So if this is my rice table, since the Y was the limiting reactant, it gets used up completely, so we'll use all of this. And that leaves none of it. I figured out on the last question that I will make 0.0248 moles of this, so that'll give me 0.0248 moles of that at the end. And then because this is a 1-to-1 reaction, I know that that's also the amount of this that I'll use in my X. That's going to leave me 0.0006 moles of X left over. So if I put all that X and all that Z together, and knowing that those are both gases, gas and gas, together that would give me a total of 0.0 0.254 moles of gases present at the end of the reaction. At the completion of the reaction, 0.0254 moles of gases, and that's X and Z together. All the Y was used up. So that's total moles, and so pressure in my ideal gas law equation is nRT over V. My total moles of gas, 0.0254 moles. My R value, got a couple choices on my constants page. I tend to use 0.028206, 0.8206. There's the units. Temperature was, the problem started out here, 22 degrees Celsius. So that's 295 Kelvin. And the volume of the container, one more time, was 2.5 liters. So there's total moles of gases, RT over V. I could figure out the pressure of each gas separately and then add them together, but I don't need those separate things, so I might as well just do this and get the total, because they'll all contribute proportionally, and that's going to give me a pressure of 0.246 atmospheres. So the total pressure in there when the reaction reaches completion from both X and Z together, 0.246 atmospheres of pressure. All right, that's a bunch of stoic. Okay. 3 possible mechanisms for the reaction. Which one's most consistent with the experimental data? And remember, our experimental data, let's see, that was rate equals K times X to the first, Y to the first. First order for both X and Y. So which of those mechanisms would allow for that? Justify your choice by writing a rate law for each of the 3. Okay. So for mechanism 1, the slow step here would include X and D, and since D is an intermediate, I would have to substitute in for D Y to the second order. So for mechanism 1, rate is going to be K X to the first and then Y to the second. And that does not work because we need X to the first and Y to the first. For mechanism 2, my slow step, let's see, is the first step, and that only has X as a reactant, so rate would just be K and then X to the first, and Y wouldn't be there at all, so that's no good. Hopefully the third one works out. For mechanism 3, I'd have a slow first step where X and Y are both reactants, so rate would be K, X to the first and Y to the first. So that's a match. Yes. Mechanism 3 is our correct choice. Identify substance D in the mechanisms shown above as an intermediate or catalyst. Well, D is formed in all 3 of these mechanisms and then used in all 3 of the mechanisms later. So if it's formed and then later used, that makes it an intermediate. It's something that's present for a while and then gone. D is formed, I would say, by an early step, and then consumed or used, reacted in a later step. Okay. Catalyst would be present at the beginning, used, and then formed again by a later step. So just the opposite. Yeah, that's right then. Okay. G. Following diagram shows the energy of a reaction as the reaction progresses. I see this is an exothermic reaction right away. Recreate on your own paper. I'm going to do it right here. Let's see. Clearly label the activation energy for the forward reaction. So the activation energy for the forward reaction would be from the starting point, reactants, to the peak. So here's my number 1. Activation energy for the forward reaction here, step 1. I could just label it activation energy forward as well. EA forward. Clearly label the enthalpy change for the reaction. So that's from start to finish. So from start here to finish here. There's my part 2 answer, or delta H for the reaction. So that's part 2. On the diagram, draw a second energy curve showing the effect of a catalyst. So a catalyst should lower the activation energy. So I need a curve that kind of goes lower here. Still with a hump, but lower. and still starting and ending in the same place, sort of like that. So step 3 is this curve here. Okay. Collision between X and Y occur with enough energy to overcome. I'm not sure what that's meant, but I think that's the idea. Overcome or exceed the activation energy barrier, however no products are formed. So it's not a temperature issue. Identify, explain one other factor that affects whether the collision will result in a reaction. So there's collisions, they have to have the proper orientation. That's the idea, I think, here. The collisions must have the proper orientation for the collisions to be effective. So, in other words, the right regions of each molecule must collide. Okay, there we go. Think about that like if you put peanut butter on one piece of bread and jelly on another piece of bread, you can't just put those two pieces of bread together any which way and make a sandwich. Like, you have to put the peanut butter side and the jelly side facing each other, and the bread has to kind of line up so that they kind of overlap just right. And otherwise you'll have a mess, or else they won't go together, and you'll be grabbing the sticky sides with your hands, and obviously that doesn't work. So when we're looking at collisions being effective, it's the right part of each particle that's colliding. Not just that the particles collide, but that the right parts of them collide. And larger molecules tend to have sites that are the important sites or active part of the molecule, and then there's other parts of the molecule that maybe aren't involved. The bigger the molecule gets, the more likely there is sections that won't do anything if they collide. So bigger molecules can have an ineffective collision quite frequently. All right, now we're on to number 2. It's a whole different scenario here. So forget everything from number 1 as far as anything that you carry over or any reaction rate laws you wrote or anything like that. Okay, done. Experimentally observed, shown to be, I think this is supposed to be first order. That's a bad typo. With respect to X. First order, remember, first order 0 means concentration will be linear. First order means natural log of concentration will be linear. Second order means reciprocal of concentration will be linear. So if it's first order, then my linear graph here will be the natural log of X time. And it's going to look something like that. But I have concentration too. They want me to draw that graph. What would the curve look like for the graph of concentration versus time? Well, I can see it's going down here by increasingly larger amounts, so that it's dropping off faster and faster. So it's going to start out going down and then get steeper and steeper. So it's something like that. Okay, so to write the rate law expression here in A part 2, we need to take into account that the reaction is first order with respect to X, and when it says to me that decomposition of X, that means that X is all there is. X is turning into, I don't know what, let's say Y plus Z or something like that. So if X is the only reactant, then it's the only thing in the rate law expression, and so decomposition means that to me. So if it's first order with respect to X, just rate equals K times X. Explain how one of the two graphs above can be used to determine the rate constant K. So remember that, let's say K is always equal to the absolute value of the slope for the linear fit. So I would want to find the slope of the natural log of X versus time graph, and then use absolute value of the slope to find K. So explain, I don't actually have to do the calculations. I could put that data into my calculator and have it do natural log of x and plot a graph and then do linear regression on it and get the slope of that graph if I know how to do that. Or I could just take 2 of the points from my data table and do natural log of x. So find natural log of 0.1, put that in here, and then natural log of, let's say, 0.043. And put that in there. And then those would be my y values, change in y over change in x, and I'd be all set. Do they actually want me to calculate it? They do. So let's do that. Okay. Let's look at the rate constant for this reaction. So I'm going to do that using those 2 values. I think is the best bet. Let's see. Have I got an equation that'll help me with that? Maybe I do. Maybe I do. On my formula sheet, there's an equation for first order reactions. So you put this down here. For first order, I've got the equation on my formula sheet. Natural log of x at time t minus the natural log of x at time 0 equals negative k times time t. So if I want the k value, I can just rearrange that equation. I'm going to divide both sides by negative t, and that will give me k on the right, I think, right? So k will equal natural log of x at time t. So natural log of x at, let's say, 14 seconds. So I want natural log of 0.043. Natural log of 0.043 at time t. Let's see. And that's at time of 14 seconds. Minus the natural log of concentration at 0, which is 0.1. So I'm using a t equals 14 seconds, just so I know what data I'm using from the data table. So this is the natural log of x at time t at 14 seconds, and then at 0. And then I'll divide that by negative time t, which is 14 seconds. Negative t, negative 14 seconds. And that'll be my k value. So I just plugged in my calculator. Let's see here. Let's say natural log of 0.043 minus the natural log of 0.1 divided by negative 14. It gives me an answer of 0.0603, and then the units on that will be, since I've got nothing but seconds in my denominator here, seconds to the negative 1. That'll be my units. My k value, and that's my value for k. So that's using the equation from my formula sheet, knowing that it's first order. So I use the second equation on the formula sheet. All 3 of those formulas on the formula sheet are in order of 0 order, first order, second order. So I want the middle one of the 3 as my equation to find, well, anything really related to the graph, but it uses natural log. So if I know first order is natural log, then I know it's the equation that uses natural log. And that's the second one on that list. All right, so that's 1. How many minutes will it take for the concentration of x to reach 0.03? So if I kind of eyeball that, well, they're asking me on my data table here to figure out this time. How long will it take to reach 0.03? And so it's going to be something more than 14 minutes. Oh, and that was minutes. Good catch. That was actually in minutes, not seconds. So I don't know if you guys caught that while I was doing it. Hey, dummy, it's in minutes, not seconds. That's a big thing to catch yourself wrong on. Good catch. So minutes. Okay. If you saw that before I did, kudos to you. But I'm looking at my data here. To reach that concentration of 0.03, it's going to take more than 14 minutes, because at 14 minutes, it's gone down to 0.043. To get down to 0.030, it's going to take even longer than 14 minutes. So just kind of in my head, I've got an idea that it's going to be more than 14 minutes. But to find that, that's my time t, basically, right? They want me to find t, the time at which it will reach a concentration of 0.03. So I can actually use that same equation again for part 2. I'm just going to do that in blue here, just to kind of keep it apart. Here I'm going to use the same equation that we had, and that was this equation right here to start out with from my formula sheet, but I'm going to rearrange it to find t instead. So t, if I just rearrange that, will be the natural log of x at time t, which is what we need to figure out. The concentration, though, the natural log of 0.030, there will be my molarity at time t, minus the natural log of, darn it, the natural log of x at time 0, which was 0.10. And then I'm going to divide that by negative k. Okay? So to get t by itself out of this equation, I'm going to divide negative k on both sides. So negative 0.0603 minutes to the negative 1. That was my k value from the last part of my work here. And so that value, if I punch all that in my calculator, that should give me the time that is required to reach that concentration. So try that. I'll punch that in my calculator, and I get an answer. If I round it off here to 2 significant figures, and I'm using 2 because this 0.030 has 2 sig figs, I get 20 minutes. It's 19.9 something something. So we're at 20 minutes. And that's units of minutes, right? Because I'm dividing by minutes to the negative 1, which flips minutes back to my numerator. So time would be 20 minutes. Now, and again, that makes sense because I predicted at the beginning that it would be more than 14 minutes. So at least I know, at least I'm close. I'm on the right track. So that's 20 minutes to get to that concentration. In a different experiment, the decomposition of substance Y at 50 degrees was determined to have the following rate loss. So it's second order with respect to Y. On the axes above, sketch the graph that's expected to provide the linear relationship. And so for second order, I remember that for second order, the linear one will be the reciprocal of the concentration, 1 over y. So that would be my y value. 1 over y versus time will be my linear graph. So this will be 1 over the concentration of y versus time. That'll give me a linear graph. And then what will that look like as far as the graph? And we know it's straight, but how am I going? Which way does it go? And if you can't remember that in the heat of the moment, then there's a way to think about it, right? What's going to happen to the concentration of y with time? Let's just say the concentration of y starts at 0.5 molar. It's going to decrease with time, right? It's going to get gradually lower as time goes on. It's going to decrease. If this molarity decreases with time, the reciprocal of molarity will do the opposite, right? Because 1 over molarity of y, if that y value concentration is getting smaller, the reciprocal will be getting bigger with time. Hopefully that makes sense. And so my graph here is going to increase. It's going to be a slope going upward. So it's going to go up something like that. Not sloping downwards, but sloping upwards, because reciprocal, 1 over a value that's getting smaller with time, that reciprocal will be getting larger with time. So that's my graph. Be sure to label the y-axis. I did that. What does the slope of this line represent? Slope here represents k. And I don't even necessarily have to say absolute value because it's a positive slope. Slope directly represents k, my rate constant. I don't know that I'd have to write that, but I'm going to write it just in case someone's being picky. All right. Temperature of this reaction was increased from 50 to 100 degrees. Predict the effect this would have on the following. So the rate of the reaction, whenever we raise the temperature, increasing temp will increase the rate of any reaction. Now again, that's not to say that it necessarily becomes more thermodynamically favorable at a higher temperature, but it will increase the rate of the reaction. And those two things aren't quite the same. It doesn't ask me to justify it predict the effect this would have. It doesn't ask me to explain why. It's good for me to be thinking, though, why? Why does it do that? Just so you're not automatically just spouting off some hopeful fact. It's kind of a 50-50. Increasing temperature will increase the rate or decrease. It could just be kind of a coin toss if you don't have to explain. So this is kind of a question I should probably put justify on there. I didn't, so this would be enough. But if it asked me to justify it, I would want to say that increasing temp increases the velocity of the particles, which means that you'll have more frequent and more forceful collisions. And that means that you'll have more effective collisions per moment, per unit of time. You'll have more effective collisions every second, every minute, every hour. If all the particles are moving faster on average, which is what temperature is, an expression of their velocity, their average velocity, then you'll have more particles that are colliding with sufficient energy for the reaction to occur. So you're right, your rate of reaction will go up. What about rate constant K? Well, just think about that expression that we wrote earlier up here. Or they gave it, sorry, we didn't have to write it, they gave it to us. If I take this expression from the beginning of the problem, if I rearrange it for K, right, K will be rate over Y concentration squared. And so if rate goes up, K will go up because it's in the numerator. And we just said that if rate goes up, or if temperature goes up, then rate will go up. We can say then that the rate constant, increasing temp, will also increase K. And increasing K because rate increases. Right, and we already said that in the previous one. It's due to because we have more effective collisions per unit of time. What will the graph look like at 100 degrees? If we add a new plot to that graph up above, what will the graph look like at 100 degrees? So this first line that we drew was at 50 degrees Celsius. They're asking now, what will the new line look like if I was to draw a new graph at 100 degrees Celsius? It's a little tricky maybe. What's going to happen to the concentration here, again, of Y, if this is my Y concentration, what's going to happen to the Y concentration as time goes on? Well, we already said that the concentration will decrease. But if the rate of the reaction has been increased at a higher temperature, then Y will decrease even faster than before, right? With time at 100 degrees Celsius. The concentration of Y will go down even faster at 100 degrees than it did at 50 degrees. It'll be used up faster than it was at the lower temperature. So, if Y is decreasing faster, the reciprocal of Y will get steeper even faster. And so it'll get steep faster. I want to draw a new slope that shows that's kind of jaggedy. I'm gonna cheat just a little bit. And I'm going to use my ruler because I've got one here. You should certainly feel free to use a straight edge, on any question. The edge of the paper that you're working with or whatever might be available to you. Turn my ruler off. This new graph then would be at 100 degrees Celsius. The rate would be faster. The K value we said here in part D2, the K value would be greater. It would be increased. And remember, K is the same as slope. So since slope is equal to K, if K goes up, slope will go up. And I've drawn in here then a second slope, the dashed line, that has a steeper slope than the first one. So a second graph or a second plot on that graph should still be linear. The order, the rate order, the reaction order hasn't changed. It's still second order, so it'll still be a linear graph with reciprocal of Y. But it will be steeper at that higher temperature because the rate went up. So plot it, done. What else? That's the end. Awesome. That is a long assignment. Hopefully you did okay on it. Again, I know a lot of you wrote me or shared with me on office hours that it took a good chunk of an hour to do, which was kind of our unofficial time limit on this. Hopefully you felt like you could get effective amount of it done. If you didn't get it all done in an hour, it's not the end of the world. Remember, we're shooting to get 3/4 or even 80% of the work correct in an hour. So if you did everything and you did everything right in that time, it doesn't matter if you finished all of it necessarily, as long as what you got done was done right. So we'll take a look at it and give you some feedback on this. As far as point breakdowns go, I haven't got a scoring guide that matches with this perfectly necessarily. So I don't exactly know how the folks that come up with the scoring guides on these things would assign the points to this. I'll go through here with you just real quickly as we end and give you the approximate points that I would say everything would probably be worth. A lot of times it's easy to kind of award extra points. The way I'll probably score it here it's probably these will be just worth 1 point each for the order and your justification. So there's 1 point each for that. 1 point for the rate law. For the value of the constant here with proper units, I'm going to make that 1 point. So with the units, if your value is right and your units are off, I probably would award a half point in my own scoring, knowing that on the actual AP exam, units with the value probably would be 1 point total, and there are no half points there. Rate of disappearance of Y, again, that's probably just 1 point. Let's see, limiting reactant with justification. I think I'd actually probably make that worth 2, especially since this is a good stoic review that we haven't done for a long time. 1 point there, and then I think I would go with, for part 3 here, for total pressure, I would make this worth 2 points, because 1 point would be for figuring out the total number of moles of gases from sort of my Rice table approach or whatever you used, and getting the right number of moles of gases. And then 1 more point for getting the pressure calculated correctly. So if your moles were wrong, but you calculated a pressure based on your moles correctly, you could still get that second point. For my mechanisms question, I would actually probably make this worth 2 points for my own scoring guide. And the way I would do that is 1 point for showing mechanism 3 is correct properly, and then 1 point for ruling out both of the other mechanisms properly. And again, I'd probably do half points on those first 2 mechanisms if you were able to rule one out correctly. D as an intermediate with an explanation, 1 point. On our graph, each of these would be 1 point. So 1 point for each thing that you add to the graph. 1 point for describing something to do with collision orientation. A simple but important idea. As we get down here, 1 point for each graph. So I would say there's 2 points here, for one for each graph. 1 point for the rate law expression. And then 1 point for your explanation of how you would find the K value from the graph. Calculate the rate constant, being sure to include units. I think I probably would actually make that 2, because that's kind of a calculation that's a pretty important one. And I would probably make this worth 1. So somehow I'd probably make part B worth about 3 points total as I'm grading that. For part C, sketch the graph that provides the linear relationship when plotted against time, and then be sure to label the axis. So there'll be 2 points there. One for the linear graph, or the fit line that's linear there, and that was our 50-degree one, and then 1 point for the axis label. 1 point for telling me that that's going to be the slope, or the rate. The slope is going to be the rate constant, or K. Point here, and then a point here, especially because it didn't ask for justification. Okay, and that's it. So that comes out to be, looks like 6 points on that page, 7 points on that page, so that's 13. 4 more points on that page, that's 17 points, and 6, 7, 8 points on that page, it's 25, and then 5 points there. So that's 33 points worth of questions here on that big assignment. That's quite a bit. All right, so lots of little details to find. I think you'll find there's a pretty good variety of concepts and topics from our unit on kinetics within this one quiz. So see how you did. We'd be shooting, at this point for a 75-80% on that. So looking for maybe a 25-26 would be phenomenal at this point. And heading into the review portion of our unit and moving on from there, just kind of give you a sense of maybe where you are with kinetics and how much more time you need to give it, and how much you can afford to start reviewing other things. Hopefully that helps. If you have other questions about your quiz or specific things that need explanation on this quiz in my key, pop in on office hours, let me know, see me with that, and I'll try to help you out more specifically face-to-face in that way. Thanks for listening, and we'll see you soon.